Okay, so in this video we're going to continue talking about circular motion, and we're going to get to the main part of this unit, which has to do with what's called centripetal force and centripetal acceleration. And so remember, this unit that we're on right now has to do with circular motion. And the purpose of this unit is because, a lot of objects don't move necessarily in straight lines, but they tend to move in curved paths or circular type of paths. So for example, when the moon orbits the Earth, or when the planets orbit around the sun, the shape of those orbits are pretty much circular. If you think about the wheels spinning on your car or your bike, or roller coasters going around in a loop, merry-go-rounds, race cars going around, driving around on a racetrack, all of those involve some type of circular motion. And so this is basically the physics of what happens when objects don't move in a straight line, but when they moved in curved paths. Okay, so just to kind of review, we talked about Newton's first law in the last video, or not in the last video, but in the last unit. And this is what we said about Newton's first law. We said an object at rest remains at rest, and an object in motion remains in motion at constant speed along a straight line unless acted upon by a net force. And so, looking at the first law, we can ask ourselves a question. According to the first law, do objects in circular motion have a net force acting on them? And the answer to that question is yes, they do have a net force acting on them. And the reason is this little bit of the first law right here. Constant speed along a straight line. Or you could also say constant velocity, and that means the same thing. We talked about this in the last video, but an object moving in uniform circular motion is constantly changing directions. And so because it's not moving in a straight line, it is in fact changing directions. According to Newton's first law, in order for this to happen, there must be a net force acting on that object. And so yes, objects in circular motion do have a net force on them, and so that's what we're going to be talking about now in the next slide. Okay, so let's talk more about this net force that's required for circular motion. Okay, so you can see on this slide, objects moving in circular motion do have a net force on them. This net force has a special name. And the name for this net force, I put it in bold right here, is called centripetal force. Okay, so for centripetal force, we write F for force, and then we do a C, a lowercase c, for centripetal force. And it's important that you know what the word centripetal means, because it will help you answer some questions. The word centripetal means center-seeking. And the reason it has the name center-seeking force is because the direction of this force, which is required for an object to move in circular motion, is always towards the center of the circle. And so here on the right side, you see a picture where an object is moving around in a circle. It's going counterclockwise, and you can see an arrow showing you the velocity of the object right here. And you can also see an arrow representing the direction of the centripetal force pointing towards the center of the circle, which would be over here somewhere. And so objects in circular motion always have a centripetal force, and that is always directed towards the center of the circle. Now, this is not a new type of force. Okay, this is not a force like tension or gravity or normal force. It is a net force. Okay, and so this is not something that would go on a free body diagram necessarily, but this is something that would be made up of the sum of the forces towards the center of the circle. Okay, usually you only have one force towards the center of the circle, though. Okay, so this is in fact a net force. Because there is a net force on such an object, that means there's also an acceleration. This acceleration has the very original name of centripetal acceleration. And it has that name because it is also always directed towards the center of the circular path, as you can see here in this diagram to the right. Okay, notice how the acceleration is always pointing towards the center. And so this A, you could also put AC for centripetal acceleration. Okay, so both the centripetal force and the centripetal acceleration always point towards the center of the circle for an object moving in circular motion. Just to show you what that might look like, I will go back to this simulation I've shown before. And here we can see a red ball moving counterclockwise in circular motion. And here the blue arrow represents the velocity of the ball. Okay, notice this blue arrow is always kind of pointed along the outside of the circle. But the green arrow represents the acceleration of the ball. And notice that the direction is changing all the time. Okay, but the green arrow is always pointed towards the center of the circle. I can actually make it move a little faster so the arrow gets a little bit longer. There you can see that green arrow represents the centripetal force and the centripetal acceleration both, because the direction is always changing, but it's always directed towards the center of the circle. So objects in circular motion have this type of force and acceleration, the centripetal force and the centripetal acceleration. And we're not going to get into the details of why it has to be like that, but those things are required for an object to move in circular motion. Okay, now I do want to remind you that centripetal force is a net force. It is not one of the individual forces we talked about in the past. You would never put centripetal force on a free body diagram, but you still have to have that centripetal force in order for an object to move in a circle. And so what that means is, in order for an object to move in circular motion, it has to have at least one or more forces directed towards the center of the circle. So in the following examples, we're going to identify which force or forces, because it could be more than one, even though it's usually just one, which force or forces are providing the centripetal force. And again, what we're looking for is which forces are acting towards the center of the circle. Okay, so take a look here. If you look at the picture on the left, we have a girl, and she has a bucket full of water, and she's swinging the bucket around in a circle above her head. Okay, now in this case, our task is to identify the forces that are providing the centripetal force. Remember, centripetal means center seeking. Okay, so the easiest way to do this is to, first of all, identify which forces are acting on the object, or really draw a free body diagram. The bucket has a force of gravity, of course, going down, but if you look at what she's holding a string, or she's holding a rope, and anytime you have a string, you have tension. Okay, and so there's actually a force of tension in that rope. I'm going to label that as Ft, and those are the only forces acting on that bucket. It's not, touching a surface or anything like that, so there's no normal force. And so our goal is to identify which force or forces are providing the centripetal force. So we need to key in on which forces are acting towards the center of the circle. Remember, centripetal means center seeking. Well, if you look at these two forces, only one of these two forces is towards the center of the circle, which is right here where her hand is. Okay, and so in this case, that is the force of tension. And so what I would say is the centripetal force is equal to, in this example, the force of tension. Okay, the force of tension is providing the centripetal force for the bucket to move in a circle. Okay, take a look at the middle picture here. So here we have a roller coaster, and we don't have to draw an FBD because they've already drawn arrows representing the forces, which is nice. Here's the center of the circle, and again, we want to know which force or forces are providing the centripetal force. And so we want to focus on which of those forces are pointing towards the center of the circle. But if you look at the normal force and the force of gravity, both of those forces are going towards the center of the circle. And so actually, both of them would provide the centripetal force. And so really, I would write Fn plus Fg because they're both center-seeking forces. By the way, if you want to know why is the normal force pointing down, remember the normal force is always perpendicular to the surface. It's always coming out from the surface. And in this case, because the roller coaster is upside down, the surface is pushing them down, not up. So that's why the normal force is pointing down here for the roller coaster. Okay, so if you take a look up here, we have the Earth going around the Sun. Again, our goal is to identify which force or forces are acting on or which force or forces are providing the centripetal force. In this case, this is a very easy question, because if you think about the forces acting on the Earth, there's only one force, and that is the force of gravity. There's no other applied force or any other forces acting on the Earth as a whole other than the force of gravity. So in this case, I would say that the centripetal force is provided by the force of gravity. Again, what I want to focus on is which forces are pulling the Earth towards the center of the circle, but if there's only one force acting, it has to be that force. Okay, in other words, if you turned off gravity, if there was no centripetal force, the Earth would just fly off into space in a straight line. Because remember, Newton's first law says if there's no net force on an object, and the object is moving, it's going to keep moving at constant speed in a straight line. So if you just magically turned off gravity in the universe, all the planets and all the stars would just fly off in a straight line with whichever direction they were moving before, which would be bad, of course. Okay, take a look at this last situation down here. This is one that you definitely need to make sure that you add to your notes, okay, because it's not at all obvious what the answer to this question is. We want to know which force or forces are providing the centripetal force, and this one is not obvious, and so there's no way I would expect you to know it without me telling you. So here's the answer. On this car that's going around in a circle, there's three forces. There's a force of gravity going down, of course. The car's on the surface, so there's a normal force going up. And if you want to know why my arrows are slanted, it's because the picture is kind of drawn at a weird angle. And there's one more force that goes towards the center, and that is the force of friction. And it's kind of difficult for me to explain why friction points towards the center of the circle, or why there's friction there. But the answer to this question is it is the force of friction that provides the centripetal force for a car to go around in a circle. Okay, which is why I said that's not obvious at all. And so there's no way for you to know that without me telling you. And so there's the answer to the question. For a car going around a flat curve, the force of friction provides the centripetal force for the car to move in circular motion. That means, by the way, that when it's icy out or when it's rainy out and the road is wet, when there's less friction, it's more dangerous to drive around a curve because that means there's less centripetal force allowing you to go in a circle. Okay, and so if it's icy out, if the friction is low enough, you can actually try to go around a curve and you can lose control of your car because there's not enough centripetal force to make you go in that circle. Okay, so that means when it's icy or when the weather is bad, you have to be really careful when you're driving your car. Okay, so pause it there and make sure you add that to your notes. Okay, so now let's look at equations for centripetal force and centripetal acceleration. Okay, both of these equations look very similar. The equations are both very easy, and so here they are. The equation for centripetal acceleration looks like this. We write AC for centripetal acceleration. Remember, the direction of that is always towards the center of the circle. And that is equal to v squared divided by r, where v represents the linear speed or the linear velocity of the object. Remember, that's in meters per second because velocity is in meters per second. And r represents the radius of the circle. Okay, the radius is measured in meters. Okay, so it's a very simple equation, v squared over r. Okay, so that means the amount of that centripetal acceleration depends on how fast the object is moving and how big is the circle. Now the equation for centripetal force looks very similar, because remember, centripetal force is a net force, and net force is always mass times acceleration. And so if you take the same equation for acceleration, v squared over r, and you multiply by mass, you all of a sudden have an equation for centripetal force. So there's only like 2 or 3 equations in this unit, and here's most of them right here. One for centripetal acceleration, one for centripetal force. Okay, so now we're just going to do some examples with these 2 equations and we'll be done with the video. Okay, make sure you add these to your notes. And of course, the units for centripetal acceleration, any type of acceleration is measured in meters per second squared. We've seen that before this year. And then centripetal force is a force, and so that's measured in newtons. Okay, we've seen that before as well. So now let's just do a few quick examples using our 2 equations. Okay, so moving on. Example 1. It says, in the image to the right, a woman swings a 4-kilogram bucket around in a circular path of radius 0.2 meters at a speed of 0.3 meters per second. The first question says, calculate the acceleration of the bucket and which way is it directed. Now, of course, we know the direction of the acceleration is towards the center because it's centripetal acceleration. So you would just say, towards the center of the circle. For the actual calculation, we just need to use the equation for centripetal acceleration. Make sure you identify your givens. Here we have the mass, so that's our m. We have the radius, which is r. And we have the speed, or the velocity, which is v. The equation for centripetal acceleration is just v squared divided by r. And so that would just be 0.3 squared divided by 0.2. And you would plug that into your calculator. And if I'm not mistaken, you should get 0.45 meters per second squared. And that would be the acceleration on the bucket, which is centripetal acceleration because the bucket is clearly moving in circular motion. The second question says, determine which force or forces are providing the centripetal force on this bucket. Of course, that would be tension. We've already seen that in another example. But it's important that you understand that because, look, the next question says, calculate the tension in the rope. Now, we don't have an equation for tension, but we do have an equation for centripetal force. So when you read that, you need to understand, hey, when they ask us to calculate the tension, they're really asking us to calculate the centripetal force because the tension is providing the centripetal force in this situation. And so here we just need to use the equation for centripetal force. That's mv squared over r. And so the mass is 4. V is 0.3. Don't forget the squared is only on the v. So you would do 0.3 squared times 4 and then divide by 0.2. And if you do that correctly, you should get 1.8 newtons. Okay, so the tension in the rope is 1.8 newtons. And then the last question, how would the tension change as she swings the bucket around faster? That's very easy to see if you look at the equation, mv squared over r. Notice that we are multiplying by speed in the equation. And so if we multiply by a bigger number, that means we would have a bigger force. So if she swings the bucket around faster, that means that v would become bigger. That means the centripetal force would also become bigger, which is probably pretty common sense, but there you go. Okay, that's the answer to example 1. Alright, so I'm going to erase this in just a second, so pause it here if you need to look at that some more. Okay, just to do 1 or 2 more examples, let's take a look at example 4 really quickly. Example 4 says, in order for a car to move around a flat curve, there must be a centripetal force provided by the force of friction between the tires and the road. And you can see a little picture showing you that. In the picture shown to the right, the maximum value for the frictional force for the 1,200 kilogram car, okay, so they're giving us the mass of the car, because that's in kilograms, is 50,000 newtons. Now remember, in this situation, the centripetal force is provided by the force of friction. So when they give us the force of friction as 50,000, they're actually giving us the centripetal force. And then they also give us the radius is 12 meters. And what they're looking for is calculate the maximum speed, so that's v, that's our unknown, a car can have to safely make the turn. Alright, so we have our equation for centripetal force, mv squared over r. I'm going to plug in my givens. Okay, so I've got my equations. I'm going to substitute. I have 50,000 for Fc equals the mass of the car is 1,200. V is unknown, so I just leave that in the equation. And then divide by the radius, which is 12. Okay, now what I would do at this point is I would simplify this a little bit before I try to solve for V. 1,200 divided by 12, I can simplify that because I can just make that 100. Okay, so 1,200 divided by 12 is 100, and so I can simplify this just a touch. Okay, so I'm going to write that as 50,000 equals 100 times v squared, and if I want v by itself, I have to ask what's being done to v. Number 1, it's being multiplied by 100, and number 2, it's being squared. So first I want to divide both sides by 100. Think SADMAP. Okay, so I do that first. 50,000 divided by 100 is 500. And that's equal to V squared. And then to undo a square, I want to do the opposite square, which is square root. So I'm going to take the square root of both sides. And so in my calculator, I'm going to type in the square root of 500. And the answer I get is 22.4 meters per second. And that is the answer to my question. And so calculations with centripetal force and centripetal acceleration are usually very simple. They're usually not complicated. As long as you understand what everything in the equation is, you shouldn't have any issues with these problems. Okay, maybe a little bit of algebra like in this problem, but more often than not, it's just plugging into the equation. Okay, so pause it there if you need to add that to your notes. Okay, so I'm going to erase this. I want you to try to do example 3 on your own. And I will put the answer in so that you know what the correct answer is and you know how to answer the question. As always, please let me know if you have any questions, and I'll see you guys in the next video.